Hello viewers, welcome back to the course on matrix computations and its application. So, in the previous lecture we have discussed about that the definition of vector spaces, and we have started with the n-Tuples Vn. So, we will continue from that one. So, in the previous lecture we have started with that let Vn is the n-tuple. So, Vn we take a space that contains the elements like x1, x2, xn, where each xi belongs to a real line. Now, we want to discuss or want to show that this makes the vector spaces. It means that we have to satisfy all the properties related to the vector spaces. So, first of all I will define that what is the vector addition and scalar multiplication in this case. So, we define the vector addition. So, vector addition is defined as usual. As usual means, suppose I take a element V1, suppose this V1 is a element and I represent that element by x1, x2, x3 and xn, and I take the another element V2 and I represent by y1, y2, y3, yn. So, this I take from Vn, this is also I am taking from Vn. Then I define V1 plus V2. So, this is the same way we used to add two vectors. So, we are adding component wise. So, that is x1 plus y1, x2 x2 plus y2, x3 plus y3 and so on xn plus yn. So, this is we call it the vector addition we are taking in the case of Vn, and that is why we call it the usual, because this is the way we used to take for addition of two vectors. Also, the scalar multiplication so scalar multiplication I am defining that if I take a scalar, so for any scalar alpha, and we know that alpha comes from the field, whatever the field we are taking in this case. So, in this case we are taking the real numbers. So, alpha is coming from the field, then I define alpha v, or suppose alpha V1. So, in this case I am taking alpha and then V1 I have taken x1, x2, x3, xn, and we know that for a given vector if we multiply by the scalar, then we can define take the scalar inside, and that becomes alpha x1, alpha x2, alpha x3, alpha xn, and this also belongs to Vn. In this case also this also belongs to Vn. So, from here that this is the way we are taking the scalar multiplication, and this is the way I am taking the vector addition. So, based on this one we want to check that Vn, so with addition and scalar multiplication just I have defined. So, we want to show that is a vector space. So, for this one I need to satisfy all the properties. So, I will show you that few properties that how we can define, but the first property is that the associativity. So, that is very easily we can define, because it is just the vector addition I am taking. So, we can take V1 one vector, V2 and V3, and then I am writing this one. So, I can define this one is equal to V 1 plus V 2 plus V 3, this one, and from here we can write that V 1, V 2 and V 3. So, this is we are defining for all V 1, V 2, V 3 belongs to V n, where V 1 I have defined like x 1, x 2 like this one, and V 2 is y 1, y 2, and V 3 I can take another one like z 1, z 2, z 3 up to z n. So, that is also we can take in the another form. So, this is very easily we can satisfy. So, this property is satisfied. The second one is that now we want to define that after the associativity the 0 element. So, 0 element means for any vector v belongs to the V n, if there exists v so I will take only v plus 0 element, then it should be equal to 0 plus v and then it should be equal to v. So, this is should be true for all v belongs to the space. Now, the question is what is the 0 element here? So, we can define the 0 element. So, 0 element here is can be taken as element with all the component 0, and we know that this belongs to V n because 0 is already there in the real number, and we are taking all the set which take all the real numbers. So, this is belongs to the V n. So, this is the 0 element, and by the vector addition we can see that v plus 0 or 0 plus v, that will be equal to the vector v again or all v belongs to V n. So, in this case this is called the 0 element, and we also call it additive identity. So, after this additive identity, now next property I want to define for the additive inverse. So, in the additive inverse for any vector v, so v I am just now taking x 1, x 2, x 3, x n. So, we could because we can give the name. So, just taking v as this one, and that belongs to V n, because earlier I have taken v 1, but now I am just taking that for any v belongs to this one. Or now we can define a vector minus v. So, in the minus v I am just what I am doing is that I am taking minus 1 multiply by v, and this will be equal to, because I have already defined the scalar multiplication. So, I can write this as a minus x 1 minus x 2 minus x 3 minus x n that is also belongs to V n, because this way we have defined the scalar multiplication. So, from here I can say that v plus this vector, or maybe minus v plus v, it can be written as 0, where 0 is the additive identity. So, this is true for all v belongs to V n. Whatever the element you take, we can take its minus of v, the additive inverse, and then this will come equal to 0. So, in this case this element we call it u. So, u is called additive inverse. Okay, so, after this the fourth property we can define is that for any element u plus v, it can be shown that this is equal to v plus u. This is true for all u v belongs to V n. The same way I can choose a element u and v, and then it is made up of real numbers. So, component wise addition I can do, and then we can just change the position of the elements. So, it becomes the commutative. So, these 4 properties are satisfied. From here I can say that this is a commutative group under addition. Then the 5th property comes is distributive property. So, I can show from here I can show that for any alpha and u plus v. So, I can define my alpha I am taking here. So, suppose u is some element there. So, I just take the element u for any u and v. So, let us we take u is equal to maybe x1, x2, x3, xn. It can be any element. V I am taking y1, y2, y3, yn. Okay, so, these 2 elements I am taking. Then alpha u plus v. So, this can be written as alpha, and u plus v I can write as a x1 plus y1, x2 plus y2, and xn plus yn. This I can take with the vector addition, and then now I apply the property of scalar multiplication. So, this will become x alpha x1 plus y1 alpha x2 plus y2 and alpha xn plus yn. Now, this alpha into x1 plus y1, these all are the real numbers, and in the real numbers I know that we can write this as alpha x1 plus alpha y1 alpha x2 plus alpha y2 alpha xn plus alpha yn. So, this one I can write, and now I can write this as alpha x1 alpha x2 alpha xn plus alpha y1 alpha y2 alpha yn. So, I am just separating the vectors, because if we take the addition, it will I will going to get the same thing, and this can be written as alpha, and now I can take the alpha common, and from here I can write like x1 x2 xn plus alpha y1 y2 yn, and from here I can write from here that alpha u plus v now can be written as alpha u plus alpha v, and this is true for all u and v belongs to V n, and alpha is a scalar, and scalar is always coming from the field. So, this property, the 5th property is satisfied. The same way the 6th property I can satisfy that alpha I am taking the scalar plus beta another scalar, and if I write u, then the same way I can show that this is equal to alpha u plus beta u for all alpha beta belongs to the field and u belongs to the vector space V n. So, this property the same way we can define. Then the 7th one we can define as alpha beta u. So, here I can write this form as alpha beta u, or I can write beta alpha u. This is true for all alpha beta belongs to the field and u belongs to the V n. So, this properties is also just the scalar multiplication we have defined, by that way we can verify. And the last one is that if I take a one element from the field and multiply by u. So, 1 and u, suppose it is I am taking x 1, x 2, x 3, x n, and this can be written as by the scalar multiplication, it can be written as x 1, x 2, x n, and that is equal to u. So, from here I can write that 1 u is equal to u, and that is true for all u belongs to the, and 1 is coming from the field f. So, this property is also satisfied. So, from here I can say that V n under the usual addition and scalar multiplication is a vector space, because it satisfies all the properties. So, based on this one I can say that this is a vector space. Now, so after doing this one, we can define another vector space. So, like before that I just want to give example that V n, you must have seen that in this case V 1 will be a real line, the whole real line, V 2 will be just containing the two element. So, it will be a type of x 1, sorry, you can write this as, okay, this will be x y, all the element x y, where x and y belongs to real number. So, this will be equal to basically r square, the x y plane, and that is x y plane. V 3 is again the element x y z, all the elements triplet, and x y z x y z belongs to the real line. So, it is the space, 3D space. So, this 3 we know, then we can define V 4, or V 4 I can define as the element x, y, z and w the same way. Okay, so, this is the fourth dimension, fifth dimension, and then we can define the nth dimension. So, this way these are the few examples we have taken for V n. Now, after that we define the another type of vector space and we call it the Pi. So, what is Pi? So, let Pi denote the set of all polynomials with real coefficients defined on the interval I. So, now we are taking all the polynomials with real coefficients, and that is defined on the interval I. So, that is a set we are taking. For example, I take a polynomial like this one p x. So, alpha naught plus alpha 1 x plus alpha 2 x 2 x square and so on up to alpha n x n. So, in this case this is my polynomial and I am taking my x coming from the interval I, where this coefficient alpha i's are the real numbers we are taking and n is a non-negative integers. So, in this case I can say that this polynomial belongs to the set Pi. So, now from here I can define a set P n x, and this one I can take the set of all real polynomials. Real polynomials means the coefficients are coming the real, the set of all the polynomials having degree less than or equal to n. In this case we have a degree n, and here I am defining P n x, a set of all the polynomials whose degree is always less than or equal to n, and I am taking this one, and x we take that belongs to some interval I. So, this is the set I have taken. Now, my claim is that, so this is my claim that P n x is a vector space. Okay. So, the question is that if it is a vector space, under which operation they are vector space. So, now I am defining that it is vector space under vector addition. So, vector addition means it is a usual vector addition, that how the two polynomials are added, and usual scalar multiplication. For example, I know that if I take a polynomial, suppose I take polynomial P1, just take 4x cube plus 3x plus 1, and I take P2 is 2x square plus x minus 1. Now, we know that if I add the polynomial P1 and P2, then the terms with the same power will add. So, it will become 4x3 cube I have taken, then x square is coming from here. So, 2x square, and then I am taking the collecting all the terms corresponding to the x. So, it will be 4x, and this will cancel out. So, that will be the addition, usual addition of the polynomials. Also, I want to define suppose 5 P1. So, 5 P1 means that scalar multiplication. So, 5 is coming from the real number, and now I am multiplying by the polynomial 4x cube plus 3x plus 1, and from here it becomes 20x cube plus 15x plus 5. Now, the question is that vector, this addition is valid or not. So, you can see that this also belongs to the polynomial P n. This also belongs to the polynomial P n. Okay. So, this is the way two polynomials can be added, and this is the way we can have the scalar multiplication with the given polynomial. So, from here I have defined this operation. So, that is usual addition and usual scalar multiplication. So, the question is that whether it is a vector space or not. So, now we can verify, or we can check all the properties whether it is satisfying or not. So, in this case, so let us check the properties. Now, so the binary operation is already there. Now, I just want to check that it is a vector space or not. So, the first property is associative property. So, in the associative property, we know that if I take a polynomial P1, I just represented by P1. So, P1 can be this. So, it is a function of x. So, just I am writing P1, that is it. It is understood that it is a function of x I am taking. So, P1 I am taking one polynomial, and another polynomial I am taking P2, and another polynomial I am taking P3, and I am doing the vector addition. So, this one if I add here, or P1 plus P2 plus P3, or P1 plus P2 plus P3. So, if I add here first and then add it to P3, or add here and then P1 and then add it to this one. So, all are same for all P1, P2, P3 belongs to the Pnx. Okay. So, this is true because we can verify from here, that does not matter whether we add P1, P2 and another P3, or P2, P3 first and then P1. This we can verify just by the taking 3 different type of polynomial of degree less than equal to n, and then because the coefficients are real, so the same power of x will be added. The second one is that I want to take the additive identity. So, the question is again comes that what is the additive identity here? It means I need a element E such that if I add to some p or E plus p, then I should get p, and it should be true for all p belongs to the polynomial set, this one. So, now from here I need to find what is my E. So, now you can from the previous knowledge of polynomials, I can define a polynomial 0 x n, 0 x n minus 1 and so on up to 0. So, it is a polynomial with all the coefficient 0. So, this polynomial is called 0 polynomial. Zero polynomial means all the coefficients in this case are 0, and we can write that this is my additive identity, because if I choose any polynomial p plus e, then the coefficient will add up, and then you can verify that this will be equal to p again. So, in this case this is my 0 polynomial and I have my additive identity. So, the third one is that additive inverse. So, in the additive inverse also I know that for any polynomial p, so suppose I take the polynomial p as, so what we have defined alpha naught. So, suppose I take a polynomial alpha naught plus alpha 1 x plus alpha 2 x square alpha n x n. So, this is the nth degree polynomial, and in this case if I suppose I add p plus e, then it will be alpha 0 plus 0, alpha 1 plus 0 and so on alpha n plus 0 x n, and this will be again the alpha 0 plus alpha 1 x alpha n x n, and that is again the polynomial belonging to the set of polynomials p n x. Okay, so, this is also true. So, from here I can say that this I need a inverse. So, I have to take the inverse basically. I will choose the inverse. So, I will choose the inverse another polynomial minus p. So, it will be minus into alpha 1 this one, and from here this will be minus alpha 0 minus alpha 1 x minus alpha 2 x square and then minus alpha n x n. So, if I take this element as I just call this element as q and this is my p. So, from here you can see that p plus q or q plus p, that will be equal to the identity that is a 0 element, this one, and this is true for all p belongs to the p n x. So, in this case the q is called additive inverse. So, this is I can define. The fourth one is that commutative. So, from here I can see that I can choose a polynomial p plus q, I can show that that is equal to q plus p for all p and q belongs to p and x. So, this one I can show very easily. So, it is a commutative group under the usual addition or the polynomial addition. The same way I can define another property. Fifth one is the distributive property. So, for any alpha the scalar p plus q, I can show or just verify, we can very easily that it will be equal to alpha p plus alpha q, and that is true for all p and q belongs to p and x, and alpha is coming from a real line R, because we are defining the coefficients are real. So, it is my field, basically we are taking the field in this case. The sixth one is I can define alpha plus beta p, that I can show that it will be equal to alpha p plus beta p, and that is also true for all p belongs to p and x field. And the seventh one is alpha beta p can be written as alpha beta p or maybe beta alpha p. This is true for all and alpha beta belongs to the field. And then the last one is that the one coming from the real line and 1 into p if I write. So, any polynomial if it is multiplied by 1, the scalar multiplication, then definitely equal to p, and this is true for all p belongs to the given set p and x. So, it means that it satisfies all the given property. Then from here I can always say that p and x, the set of all the polynomials of degree less than equal to n under the usual addition and scalar multiplication is a vector space. So, now we stop here. So, today we have discussed two main examples, the vector space, that Vn and the set of all the polynomials of degree less than equal to n, and we have shown that how we can check that whether the set is a vector space or not. So, in the next lecture we will continue with the concept of vector spaces. Thanks for watching. Thanks very much.